So yeah, as a prerequisite, in the first half an hour, we're gonna work over some theoretical aspects. So please download the repo, the dataset also, and install Miniconda because we will need it for the next hour in which we're gonna do a workshop, like hands-on coding. So the main topic of the workshop is GANs, Generative Adversarial Networks, and we're gonna code some of them in TensorFlow. I'm not gonna go now in the details. So what I wanna do is start with something really, really basic, with basic math stuff, and get you in half an hour to simple neural networks, to CNNs, and then GANs. So the first thing, or the first important thing, let's see if this is going to work. Yeah, it's the dot product. So basically, the dot product is the way you multiply two matrices. As you see, you can get the rows, you can get the columns from the other one, you multiply each item, and then you sum it. And that's the way in which you can get a new matrix. This is going to be important for the next steps in the neural networks. It's used a lot. Like, this is the main operation, I think, that's used in constructing neural networks. What's important about this is that the column dimensions from the first matrix and the one from the second, the rows dimension from the second matrix to be the same. After the dot product, another important thing is the system of equations. So maybe the first time I saw the dot product, I was thinking, okay, who invented this way of multiplying matrices? And then I started to look, to dig, and definitely it seems that's about the system of equations. So mainly, as you see in this video, let me just play it again, you have a simple system, and then you can extract it in matrices to build the same system and solve it, and this works way quicker, especially with vectorization. What's important for us? Normally in an equation you solve for the x, y, and z. We are going to solve for the parameters. The parameters in our case are going to be the 0s, 2, and 5, for example. So this is the second step. Then we have linear combos. This is more linear algebra stuff. So you have the equation of a line, which is the top one from here. Y equals with m or x plus b. And you can see in this short video that you can build, let's go back here. You can build any line if you change the m and the b. And this is going to be important for the classification step that we're going to go next one. So you can represent any line, almost any line with a given x if you change the m and b, if you tune them. So we talked about the equation of a line, but you can go even further to have the equation of a plane or even more complicated ones for bigger dimensions for hyperplanes. Data. For the data, let's say we have some linear data. What that means? It means that it's data that can be separated by a line. Yeah? And in this video, we can see that by tuning the W and the B, in the end, we can find the line that separates perfectly the two types of data, the X and the bullets. But we also have nonlinear classification. That means data which cannot be separated only by lines. So for this one, we will need a circle. Still, we can use a trick to estimate the nonlinear function, and we can do this by just using stacks of linear combinations. Yeah? And you just input the first one to the second one, and you go like this, and again, you can do nonlinear classification with linear combinations, stacking them up together. So now we arrive with the dot product, getting the linear equation, and the way you can build nonlinear functions, we get to the perceptron, which is the basic unit in a neural network. So what's the perceptron? So basically, the perceptron is just a linear combination, as I showed you, but using matrices. So you have the inputs, which are x and w. Let's go back, because I should have stopped. See? Yeah, the three x's. You have the weights, which were m before, but now are w's. And then, this should stop there, because I have two videos. I don't know why it's not working, but we'll go until the end. Anyways, here, each x is going to be multiplied by its w, and then you're going to sum them up. And something new that adds up, especially in this part of a perceptron, it's an activation function. So besides the linear combination that we saw, which can be an equation of a line, of a plane, or of a hyperplane, you also are going to have some activation functions in which you pass the output from the linear combination. And those are the ones that decide the final output for a perceptron. So these are three types of activation functions that exist: the sigmoid, the tanh, and the relo, and we're going to use them in the workshop. And they decide the final output of each unit. So basically, a perceptron is a unit. It's a basic unit in a neural network, and it has the linear combination. And besides the linear combination, it also has an activation function that you can use. So now we come up to neural networks, which is units and layers. That means more perceptrons stacked together. So as I showed you before, you can have only one perceptron, like this one, but you can also stack together more than one perceptron in one layer, as we do right now. Yeah. So in this way, you can create more complex functions. And that's how a neural network is built. You remember that I showed you the way you can stack together linear combos to do a nonlinear classification. So basically, a neural network is just this. You stack a lot of this up. Each bullet is a perceptron or a unit, and you can model them in different layers. So here, for example, we have 2 layers and an output layer, and each layer has a number of units. The first layer has 3 units, the second one has 4 units. Each one of them is a perceptron. So how do you train a neural network? How do you make it learn to predict your output? So this is like the most tricky part in neural networks. Let's go back. The final goal is to get predictions that match the labels that you have. So now we are talking about supervised learning. That means that you have the data, and the data has some labels. For example, you want to recognize cats in a picture. You have the pictures, and then you have the pictures labeled with the ones that have cats are labeled with 1, let's say, and the other ones are labeled with 0. And you want to build a neural network to train it to be able to predict cats in the pictures that have cats, and to predict that there are pictures that don't have cats in the pictures that don't have them. So this is like the goal of supervised learning. Yeah, so we have the inputs, and when the input comes into a perceptron, it gets multiplied by the weights, as we saw previously, and each input has assigned a particular weight that's multiplied by. That's important. Those weights, the W's, are randomly initialized, and as the network learns more about what kind of input data leads to the desired output, it's going to adjust the weights based on the previous weights errors in categorization. We're going to look more close at this in a moment. And then they're going to pass them through an activation function, which decides in the end what's going to be the final output. So this is the more in-depth part. So basically, you're going to have a final error, gradient descent, and backpropagation. I think I'm going to go more deeply for all of them. So you have the final error. So we said that we have supervised learning. Yeah, and supervised learning means giving to a model some data, label data, and then training him to predict those labels. You need first to encode those labels. Why? Because basically the neural network, it's a mathematical model, and it works with numbers. So to make those relations work, you're going to need to encode them. And let's say, as I gave an example before, let's give to the images that have cats 1, and to the images that don't have cats 0. Yeah? So this is a simple binary classification. Then you can use the output of the last perceptron, put it from an activation function, the sigmoid one, for example, and to make a prediction about what's the state of the picture. Does it have cats or it doesn't have? How do you do that? How do you train it? So you give true data to the neural network. Yeah? True data means data labeled and correctly labeled, and you tune the weight. The neural network starts to tune the weights so that they match those labels. This is like the intuition behind the neural nets. And in the end, you can measure the predictions quality, and this is done really simple. So for example, for one prediction error, y is going to be our label, the one that we have from the start, and y hat is gonna be our prediction. And remember that each one of them, so y can be either 1 or 0. Y hat is gonna be between 0 and 1 because we pass it through a sigmoid function. And then you can just subtract and square them so that we don't get a negative error and see exactly what's the error for that prediction. Now this needs to be done for each image. So we have this formula which is called the sum of the squared errors. What's important here to see is that this y hat is the only part that we don't have in the beginning. And this y hat, it comes up just by multiple nested functions of linear combinations. You should remember this part from the perceptron and the linear combos that we showed before. So actually here you just have the y's, the parameters, the x, which is the image basically, the pixel in the image, and the activation function, the f. And when we look at the error like this, we understand that the error, and this is the most important part in here, that the error is a function of the weights. So basically the only thing that we get in the error function are the weights as parameters. So then what we need to do to be able to make the error as small as possible is to find weights that minimize it. Yeah, so this is a technique called gradient descent. And what it does, basically we can find using derivatives what's the slope of a function. And finding this helps us because we can see exactly in which direction we need to go so that we can minimize the error. For example, here we have the function, the output of the error function, and just one weight. Normally in a neural network you would have like thousands or millions of this. And you can go in the opposite direction of the gradient, and by doing this, by finding this value, you'll be able to update the weights properly. So you do the weights update, which what means this is that you use the previous weight and you add to it the step that was calculated for the gradient descent part, and this is the new weight. So basically this process is able to make the neural network learn. So you feed the input, the neural network has some weights, some initial weights, it gets an output. By taking the derivative you can see in which direction to go to minimize the function. And by doing this, you can find the value that you need to have to update each weight in the neural network. Now, when you go with the weight step, you see that this, as I showed you before, the delta yi, it's just a proportional, it's going to be proportional to the gradient. Why is this? Because it's just the partial derivative of the error with respect to each weight. So as I showed you before, we have this function. We go here. Yeah, and we have the weight. This is the only part that we are getting in. And given that we only get in the weights, that means, and those are the only ones that can be tuned, that means automatically that it's going to be proportional with respect to each weight. And this is the formula that you use. So basically you just have the partial derivative of the error function, the sum of the squared errors that we showed before, and you do it, the partial derivative, with respect to each weight. Also, I've added here the learning rate. This is an important parameter, hyperparameter in deep learning, and not only. And what this does is just, the learning rate just sets the size of the gradient descent step. So how big is the step that you do in the minimum direction? So to calculate the gradient, you need to use multivariable calculus. I'm not going to go now into details here, but basically, given that you have multiple nested functions, for this you need the chain rules. Yeah? And using the chain rule, you can calculate the derivative with respect to each weight. And after you do all this calculation for a simple neural network, you find that the derivative of the error, the sum of squared errors with respect to each weight, is going to be this formula. And f is just a different derivative of the linear combination from there. We also add the learning rate, as before. And this is the value that we are going to use to update each weight in part. Yeah, here I'm just changing. As you saw previously, I have y minus y hat multiplied with this function, and I'm just replacing it with d for simplicity. And then to be able to update in the gradient descent step, you just use this formula, which is the learning rate multiplied with the formula that we saw before, and you also need the inputs here. So now, an important part is that we calculated the update step in the previous slides only for the output unit. Yeah? So we saw the sum of the squared errors only, and we saw how to calculate the gradient only for the sum of the squared errors. But as we saw previously, a neural network, it's built with multiple units and multiple layers. So you have all of them. And you would need to make a proper update, and to proper train the network, you would need to update each unit in part. And the question is, how do we propagate this update to each of the layers? This is one of the important questions that we need to look at now. So here you use backpropagation. This is the technique used to propagate the error back in each of the perceptions or the units that the neural network has. So what does this mean exactly? So this is the formula. It's really similar with what you've seen before. Just don't look now for the superscripts and subscripts. It's just, again, the error which we calculated before using gradient descent and the derivative. But we also use the weights here. And this is important. This is really important because we'll see in the next slide why this is important, actually. When we look over the backpropagation part, we need to think, okay, we have the final error, which is the sum of the squared errors of the final output. Yeah? So this is like only this one. How do we see how much each unit has contributed to that error? And if you take the derivative of each of these units, you're going to find out that that derivative corresponds to derivative of the previous layer, the error from the previous layer. So we're talking about this, how we calculate this one. So it corresponds to the error from the previous layer multiplied by the weights, which are used to connect the previous with the last layer. And to this, we also add the inputs that we have to this layer. So this is how we can propagate the error back in each of the units. Now, think of this like flipping back the neural network. Yeah? So this is the output normally, and this is the input. Just flip it back, and you just get in the neural network the output error, the sum of the squared errors, and it's going to propagate back to each of the units, and those are going to be updated correspondingly for how much they contribute to the error. I mean, this makes sense. If you just get a final error, right, that error is constructed by each unit in part. And each unit contributes to that error. How much? The only thing that we can change are the weights. So then the weights should be the only part that can contribute to the error, and we can use them to find back how much each unit contributes to it. This is backpropagation. Let's go next. Yeah, this is another schema for backpropagation. So basically here you have the neural net with the operations, the forward part of the network, and here you have the backpropagation part with the red, which calculates and propagates back the weights for the neural network. So after we've seen how neural networks work in general, let's look at CNNs, which are a particular type of neural networks. Now, the biggest problem with the feed-forward networks, that's how they are called, the basic ones that we saw until now, is that they are not able to retain structure. And that's important because when you feed a picture to a neural network, the picture has spatial structure there. And you can use it for your own advance to be able to predict more better. And this is where CNNs come into play, convolutional neural networks, because they add structure to the network, which is really important. And they do this by adding two types of layers, the convolution layer and the pooling layer. And we're going to look really short on this part. So as we said, convolutional nets can retain spatial structure. This is the most important part of the CNNs. And how they do this, they use convolutions, which have a lot of characteristics, and we're going to look over them also when we're coding. And they also use max pooling layers. What we saw until now in the last slides, so all the perception that we saw until now and the networks that we saw were fully connected layers only. That means that each input is connected to each of the next layer that it has. So for example, if we have one unit here, and the next one has 3, that means that this unit is going to be connected to all 3 of them. That's why it's called fully connected. For the CNN, we use also convolutions and max pooling layers. What does this mean? Let's see. Okay, so basically a convolution, what it does, you define a window. This is 3 by 3. And the window is going to have some random weights here, initialized. And you're going to slide the window over your image. So this is the image. And you're going to compute for each window a linear combination. And you're going to store the result in a new matrix. So this is how it looks. You just slide it. And in this way, what you're going to do, you're going to be able to just store the most important features from the picture. Yeah, so you have the linear combos, which are used here for getting this value. You have same weights per window. So you see that this window is slided over the entire image with the same weights. This is important. Why? Because through this is able to recognize the same feature, let's say a line, through all the picture. And another important part is that you define a lot of this. So you define, like, let's say 32 or 64, and this increases the depth of the image. So if you have the initial image somewhere at, I don't know, 100, let's say 28 by 28 by 3 because it's RGB, you would add another depth, another dimension to the image with how many features you want to recognize, how many windows you have. And this layer, it uses an activation function of ReLU, which we're going to look in the workshop. So this is what's happening. So this is the window, for example, and this is going to be slide over the entire picture. In the first phase, it's just going to recognize lines. So this should be here. I didn't put a layer. And afterwards, by combining them, the next layer is going to recognize like the nostrils from the nose, like parts of the eyes, and all this kind of stuff. In the next layer, they're going to be put together as nose, eyes, and mouth. Now, this is just the intuition. This is all numbers behind of this, but just to get how the learning part works in a CNN, in a convolutional neural network. And then we have the max pooling layer. So the problem is that in the end, we need to get only one value. Yeah, the probability of being a cat in the image or not. So we feed in the beginning a big picture to the net. So we need somehow to make it smaller. And to do this, we're going to use max pooling layers. So the convolutional layers recognize features from the image and make it more in depth. On the other side, the max pooling layers are just shrinking the image. And they are just taking the max over a window. So this is, again, pretty simple. 6, 8, 2, there should be 3 there, and 4. Yeah? So just reduce the dimensions by taking a function of max value over the window. They just take the max value. And this reduces the image so that we can get the final output. And as we saw previously, we have the fully connected layer, which is used in the end so that we get one probability only with an activation function of sigmoid. Sigmoid, basically, you feed it any number, and it gives you the probability between 0 and 1 for that number. And you have the output, the final output. So this is how it looks. You have a convolutional layer, which increases the depth. You have then a max pooling layer, which decreases the image. Another convolutional layer, which increases, again, the depth. Another max pooling layer, which decreases the image. And you do this how many times? I mean, this is the tricky part where the machine learner comes into hand to figure it out what's the best architecture for the network. And finally, you have an output layer, which is the fully connected one, and it just spits the probability out. And here you have activation functions between all of them. This is the CNN. Some improvements that are used in the CNN. One is dropout. So what's dropout? You don't want your model to overfit to your data set because your data set is just a sample from the entire population, yeah, from all possible images with cats. And after you train the model, you want to use it on new images which you didn't give to your model during training. So it's possible, if you don't do things well, to have the model do really well on minimizing the error on the training set, but when you come on validation or the testing set, which you use, the new images, is going to do really worse. To prevent this, you're going to use dropout. in each layers, and we're going to look this for this, I think, in code. We have an example. And also, another important part, so dropout is for overfitting to prevent, and there's another part, important, batch normalization, which just helps the network train faster. So basically, think about that you have the weights, and most of them were going to be close to 0 or clipped to some value. And if the weights are really, really low, when you do all the computation, because the network is really big, it's not going to be able to learn because they're going to get closer and closer to 0. This problem for, especially with the weights, it can happen in two situations. Either you have values for the weights which are bigger than 1. If you multiply them, finally they're going to go to infinity. If you have them smaller than 1, they're going to go to minus infinity. So to solve this problem, we use batch normalization. And finally, we get to GANs. GANs, it's just using two CNNs, two convolutional neural networks, that train together. And what does this mean? We're going to look closer in code, but just to give you the intuition, both of these are CNNs, the generator and the discriminator. These are the names of the networks. And for the generator, we have an unsupervised learning task. That means that we just give images without labels or data without labels. We just give some input noise, which is just random noise taken from a Gaussian distribution, for example. And you stack convolutional layers. But these are a specific type of convolutional layers. They are transposed convolution. So as we saw, the previous convolutions were able to make the network increase in depth. These ones are doing the opposite of the max pooling. The max pooling shrinks the image. Convolutional transpose makes the image bigger. Why we need this? Because in the end, we want to spit out a fake image. So you have this entire network built with convolutional transpose. And in the end, it's going to generate a fake image. But then you have the discriminator, which is a supervised task. Why? You give to the discriminator two types of inputs. One is the images labeled, which you have previously have. So these are the images that you want to generate in the end, like faces. And besides this type of images, which are real and they are labeled, you also give another type of input, which are the fakes images, and these are also labeled by you with 0, for example. So these are 1s, these are 0s. And you train the discriminator in such a way, this is a particular, a simple CNN network, as you see, convolution, max pooling, convolution, max pooling, convolution, max pooling, and the output layer. And you train the discriminator in such a way so that it's able to recognize between the real images and the fake images. So this is like in top-notch what's the most important part about the GANs. And the insight is that you're going to use the error from the discriminator to give feedback back to the generator. And the generator is going to update its own weights based on the error that the discriminator makes. And this is important because in this way, in the end, the generator is going to be able to generate real images, close to real, and the discriminator is not going to be able to classify between real and fake images, and is going to give a 0.5 probability ideally. That means it's like between Jan Goodfellow, when he explained this, he said that it's like between cops and the people who are trying to make fake monies. So the people who make fake monies, like the generator, are just trying to make fake monies that are really close to the real ones. And the police, in the same time, tries to find new methods to discover the fake monies. And this is a loop in which you get, and in this process, both of the parties get better and better at their task. And in the end, you're going to be able to toss out the discriminator and just use the generator for generating faces or other types of data. So this is the theoretical part that I want to look over it. And now, yeah, let's do a small recap. So we started with the dot product, and we saw the history of it from the system of equations, but we solved for W and B. Then we have the linear combinations, which is linear equation and adding dimensions we could get for plane, equations for plane or for hyperplanes. Afterwards, in the third point, we looked over classification. So we have like linear data, which can be classified by a line, and nonlinear data, which can be classified by multiple lines, as we saw in the previous slide. Then we have the perceptron, which is the basic unit. So the perceptron basically is constructed using the linear combinations from before, and it has also added an activation function as its final output. Neural networks, they are just more perceptrons stacked together in units on rows and layers on columns. It's all about connections in this part because they are connected together. And in the end, we looked over training with the gradient descent part for minimizing the error and the backpropagation, which propagates the error back for each unit. Also, we looked at CNNs, convolutional neural networks, which are good because they retain spatial structure, and they use two new types of layers, convolutions which give depth to the image, and those are the features that are recognized in the image, and max pooling, which shrink the image. And we also looked at GANs, which is just like a zero-sum game, can be explained in the theory of games, game playing, and it's just two neural networks, the generator and the discriminator, and they are trained adversarially. And the generator uses the error from the discriminator as feedback. And now for the second part, let's code. Yep. So I'm gonna share my screen. Let's see, how much time do we have left?
Exactly. We had 30 minutes.
Oh, cool. Yeah. So if you downloaded the data, let me check the other one. Yeah. So basically, if you've done the steps, let me just go over them again. So is it seeing? Yeah. Okay. Let me see if I can get it bigger. So if you downloaded the data, you need to put it in a folder. Let me show you. Let me just go back to my project only. Oh, yeah, here. So normally you should put the data in a data folder, as I have it here, yeah, in the root of the project, if you downloaded the repo. And afterwards, let me just copy my data there and extract it. Should go really fast. Okay. And afterwards, you should have followed the Miniconda installation instructions. If someone else needs Miniconda to be installed or wants to follow through, we can give them some sticks. Just raise your hands. And also for the workshop, we have like 6 people here who can help from Yopeso. So if you need help with something, just shout or raise your hand, and it's going to be solved, hopefully. Besides this, if you've also installed Miniconda, you have the data, then we can just really simple run the Jupyter Notebook command. And let me just show you. Yeah, this is the command that I've run. Jupyter Notebook GANs workshop, and it's going to open a notebook. So I'm not going to go into details regarding the Jupyter Notebook. Basically, this is an entire environment used for the data science and the research part, in which you can have also cells with just text, which is just Markdown. And also you can have code here, for example, as you see. And the most important part for you guys is Shift-Enter. That's how you run a cell. So that's the most important part for today. And also a really good trick for what we're going to code, Shift-Tab. It's going to give you the documentation of the functions, and just tab is autocomplete. That's really important. So you can look over this part more if you want afterwards. I have some important details here. And these are just some architecture schemes for the generators and the discriminator for the GANs, just to see what I'm talking about. So here you see we add in a random noise, and then it gets with the convolutional transpose bigger and bigger. It spits out an image, and that image is given as input for the discriminator. The discriminator also gets, besides the fake image as input, it gets real images as input, and the final error, yeah, because he's classifying between fake and real images, the final prediction error is gonna be given as feedback for the generator to train. These are 2 other schemes for it. And now for the coding part. Let me see if I have my data, because else it's not gonna work. Yeah, the interesting stuff is that I don't have the NIST data set, so let me just put it here from my side. I think I have it on a stick. Let me check. these are just some imports. Yeah, so we use the OS for operating system interface. Glob is a Python library that just uses Unix style pattern expansion, matplot for visualization, and we use matplot lib inline so that we have the images in the notebook, because else they're going to be open in a separate window. NumPy is really cool. It's a Python library that's used for n-dimensional array vectorization and also broadcasting. You can check for this more. And I also have some utility functions which are in here so that we don't go over the pre-processing part. So let me just restart my kernel to be safe. Yeah, if something goes wrong, you can just, you see that the notebook doesn't work anymore, you can just restart your kernel from kernel restart. Let's see. Okay. I'm gonna copy my data. Cool. Extract it, and now it should work. Take some time. And what I'm doing here is I'm just checking to see if you have the data put in the correct directory in the repo. Yeah, so it should be on a data directory, and the folders should be named as they are extracted, like image align celeba and NIST. So please don't change the names because I'm looking for them. Okay, so now we have the two of them. Hopefully I've put them in the correct repo because I have a couple of them. Yeah, so the NIST and the data set and the celeba data set both are found. So let's go over the images first and then over that part. So basically, NIST data set it's just a bunch of handwritten digits, which we're going to use to train the network. And the celeba, there are over 200,000 of images with celebrities. These are color images. The other ones are black and white images. And here I'm just printing some of them. So as you see, for the celeb A data set, we are interested only in faces because we want to generate just the faces from these images. So then we will need to do some pre-processing. This is done in the utils part. I have some functions there. There's a class dataset that does this. And if we work with the getBatch method, we're going to just crop the faces and resize them to 28 by 28 pixels. And now, building a network. Here's just checking for the Tensorflow version. And for building the network, we're going to build it in Tensorflow. So basically, Tensorflow uses a graph computational system to build the neural network. What does this mean? Think about it as each operation that can be done is like a unit in the graph. Yeah? And you're going to build the entire graph with all the operations that you want to do by kind of in the code by wrapping one over the other. And in the end, doing this, you're going to be able to train the network. So in the first phase, we're going to need the inputs, right? We need to give some inputs to TensorFlow. These are the images, the real images, and also the fake images that we have from the generator. I've already built the input real, which are the input, real images. And for this, we're going to use the TensorFlow placeholder. We need to give it a type of float 32, and then the shape of the input. So we have the image width, the image height, and the image channels, which is going to be 3 for the colored ones and 1 for the other one. And none here, this is important because it's the batch size. What's the batch size? So normally when you train a neural network, you're not going to train with one input on turn. So if you have 200,000 images, you're not going to use only one image. Because we use the matrix for multiplication, you can use bigger matrix dimensions, which can help you to train with more than one image at a time. So then you have a batch of images. And this none here is going to be defined at runtime. And it's just a number of images that you are going to use for each training loop. Yeah? And now what we need to do, as the to-do says, we need to create the noise input. This is the input that is going to be given to the generator. And for doing this, we're just going to create a variable input noise. If someone wants to code it as a placeholder, as I said, tab, it's really cool for completions. We give it float 32, none. And for this, we just have the dimensions as a parameter for the function. It's the noise dimension. Yeah, and it's just it has rank 2. The rank of the images, it's just of the matrices, is just the dimensions of the matrices. So this has rank 4 because it has 4 dimensions. This is rank 2 because it has only 2 dimensions. And let's just give it a name like input noise. Yeah. Afterwards, if I uncomment the test, it's not gonna work, and let's see why. Because input noise, it's not defined. Yeah, I have inputs noise. Typical programming stuff. And then after we've built this, so let's look over it again. We have the input, the wrapper input as a placeholder for the real images, for the noise part, and then we have it for the learning rate, which is gonna be changed because we're gonna use an optimizer for this. And we just return them, yeah, the real, the noise, and the learning rate. Please uncomment the test, and this should pass. Now we're gonna build the discriminator. And as I've said, let's look over it again here. Yeah. The discriminator, it's just a CNN, yeah, convolutional neural network, which uses convolutions and max pooling layers. So it uses both of them. In our case, I've mostly defined the code, so we'll just need to make one layer. So I'm just gonna go over the code to have an idea what's happening here. You have the input images, which are, for the discriminator, are fake or real. And then besides this, you also are gonna have a lot of layers. So the first layer, it's gonna be a convolution. In TensorFlow has like a couple of modalities to define the convolutions. So this is like a top layer, the easiest one, I would say. It's built over in resemblance with Keras, which is another library for deep learning, and a wrapper over TensorFlow or other libraries. And this is how you build the convolutional layer, a 2D one. Yeah, this is just tf.layers.conv2d. You give the inputs, which are the images, and then you give the filters. What's the filters? The filters is just how many perceptrons you want to have in that layer, the units, the combos, the linear combinations. In our case, they are going to be windows of size 5 per 5. With the kernel size, you give the dimension of the window, and the strides, it's just how many pixels do you want to slide the window over. Yeah, so if you remember, we have the window, and you can slide it over 2 pixels if you want, or just over one of them. Padding is, again, I'm not going to go now over it. You can ask me afterwards because it's really easy to figure it out. And as I said, this is the linear combo, the conv1, but then you also have the activation function. And we said that we're going to use the relu function. The relu function is basically if the input of the function is lower than 0, it's going to output 0. If the input is greater than 0, it's going to output the input, the value. Here we're going to use leaky relu because this helps on training. And what this means is that instead of taking the maximum between the value and 0, we take the maximum between an alpha parameter, which is 0.2, and we multiply it by the values from the convolution 1. So this is going to be a value close to 0, but not quite 0. This helps for training. Afterwards, we take the relu 1, which is basically the output from the first layer, yeah, which has 64 units, and we feed it into the second layer as input here, and we give it 128 feature maps. Again, a window 5 by 5, and a stride of 2 by 2, padding same, and here is just the weights. How do we initialize the weights? So you can pass the kernel initializer, and this is just a Gaussian distribution with a standard deviation of 0.02. Afterwards, you remember about the batch normalization. We take the inputs from the convolution, the second layer, and we normalize them. And this is done by just applying tf.layers.batch normalization. And it's important to do this only during training. Yeah, and that's why we pass training through here. Then you have the maximum, which is again the relu activation for it, and you pass the output from the batch normalization. The same thing for the next layer, gets input relu 2, more filters, that means more features that can be discovered in the images, kernel size 5 by 5, 2 by 2, normalization, maximum activation as leaky relu, and now we are gonna build the next layer, yeah, which is just the same thing with the input from relu 3. So to build a layer, first we need to build the convolutions, yeah, and I'm gonna define conv4, tf layers conv2d. As inputs, we're going to pass the previous ones, the rel 3. As filters, I'm going to pass, let's see how much I've put here. So this is going to be even bigger, the depth. More features, yeah, and I'm going to copy paste from here, it's easier. The kernel side, the straights, the padding same, and also the initializer. This should go over here. Yeah, I think I have one of them. And this is going to give me the convolution layer. Afterwards, I need to do the batch normalization, which is just the previous line of code, and we give us input conv4 and training true. And don't forget to change bn, batch normalization, to 4. And then the activation part, which is just rel 4, and we pass the bn4 here. And this should be the layer that we built, the 4th layer. Finally, as I've said, we give as input to the discriminator images, but we need to output just one number, a probability between 0 and 1, which tells us if the image has the desired feature or not. To do this, we need to shrink the image. So finally, after we get to the last layer, the convolution one, we're going to do a reshape. Yeah, and this is going to reshape the 3-dimension rank matrix of the convolutions into just 1 dimension. If you pass -1 here, it's going to get already the batches automatically. TensorFlow knows how to do this. And also NumPy behind it. So this just reshapes it to 1 dimension. And then we add a fully connected layer, the one that we discussed in the beginning in the neural nets. And we pass F5 as inputs to it. Just 1 unit, again, because we want 1 value in the end, the probability. And we initialize again the kernel for the weights. After this, as I told you, we can use Dropout for preventing overfitting, and this is used with TF layers, Dropout. You pass the logits to it, and you pass a rate of dropout. So 0.5 means that there's 0.5 chances of dropping each unit from the fully connected layer, each perceptron to not be trained. So it's like that perceptron, it's closed down, and it's not going to be trained in that run. And afterwards, we need a sigmoid. As I told you, the sigmoid, if you pass any values to the sigmoid, is going to return back a probability value between 0 and 1. And we need this to make the final output a probability, which gives the classification for us. If I've done everything correctly, which I didn't, and let's see what's the problem. Okay, I think it's definitely it's going to be something here. Let's check. That should be okay. I've put the convs 4, bench 4, the rel 4. Yeah, I forgot to pass. You need to do this. I forgot to pass the tensor for the reshape part. So you need to pass the convolution layer, the rel 4 one here. Whew. So now we are done with the discriminator. We just output both the logits. So the logits are just the output without going it through the sigmoid function. They're just the combinations, the linear combinations. And the final output is the probability. So it's the logits passed to the sigmoid. We need this for finding the error. TensorFlow needs it. Then for the generator, we need to do the same thing again. So the first layer of the generator is going to be a fully connected layer. This is important. We had a fully connected layer, if you remember. Let me try to do this. Okay, so we had a fully connected layer here. TF layers.dance. This is how we created. And this is what we need for the first layer of the generator. Yeah, and we need to give it a dimension. Let's see, units. This is what we need to give it. F1 as input. Well, for us, it's just the input noise because that's the input. Yeah, and we again initialize it with the Gaussian distribution, the weights. After we did this, we are gonna name it F1, and then we need to reshape it. Yes, so we have one shape, one dimension now. We're going to reshape it to 4 dimensions. And we're going to do this again using reshape from the previous part. Yep, and I think here we need commas, yeah, and F1. And this, I'm going to pass again F1. So this just reshapes the tensor to 4 dimensions because we want images, right? In the end. And then we need to add the batch normalization for this. Again, I'm going to copy paste it. Someone should shout when we have 20 minutes left. Just to be sure. Okay? And we have the batch normalization for this, which is bn1. And afterwards, we pass it through an activation function, as we did until now. And this is going to be a relu1, leaky relu. Just be patient to pass the proper values. And we have relu1. This is the first layer that we created. And the second one is already created. We just need to pass the input from the first one. And here, as I told you, we don't use conv2d only. We use conv2d transpose because this is going to make the image bigger. Yeah, if you look, we pass it 4 by 4 and after as input, and after it gets the output 7 by 7. Then we pass it 7 by 7, it gets 14 by 14. So the convolutional transpose is able to do this. So here we define 56 layers and a kernel size of 4 by 4. This is a window. And the slides are going to be 1 by 1, the strides. And padding, it's important to put valid. The initializer again. Batch normalization as usual. Activation function as usual. The input goes to the next layer, the third one. This is same thing. And now let's create the 4th layer. For the 4th layer, we need to use, again, transpose convolutions. Let me just put it here. This needs to be 4. We need to pass it the relu3 input, the previous input. And we need to pass it 64 filters or feature maps. A kernel size of 5 by 5, 2 by 2. And the padding needs to be same. We initialize the from normal distribution then. And we have a batch normalization part, which is here. And we need to pass the transpose conv4. The training is going to be isTrain, which is used. I'm not going to go now into details with this. We can go afterwards if we have time. And an activation function, the relu1 again. Here, I forgot to change bn to bn4, and relu to relu4, and bn4, bn4, bn4. And pass the relu4 output to the inputs part. So what we do in the output part, we want an image. And we want the fake image to be the same dimension as the real image, right? So the real image in our case is 28 by 28 by 3. So we want the output of the discriminator of the last output again of the generator to be 28 by 28 by 3. And that's how you need to model the windows and the strides so that you get this final value. And this is what happens here with the last layer, in which we pass the output dimension, yeah, which we have them passed as an input to the generator function here. And alpha, it's also passed here as before. And this is the filters, how many we want. And we also need to give the proper kernel size and the strides so that we get as the output 28 by 28 by output dimension, which in our case is going to be 1 or 3, depending on the type of image. If we uncomment, fingers crossed, test passed. Cool. So now we are in the get model part, get model loss. So we've built the 2 functions for building the generator and the discriminator, the networks. We've also built the function for the inputs, yeah, that creates the placeholder for the inputs. Now we need to start to put them together. And how does TensorFlow do this? So in the first part, let's get the generator. So this is just the generator from the function that we created. We pass again, the input noise that's passed to the get model loss. The output dimensions, which again are passed, isTrain needs to be true. And because this is gonna be for the training part. And alpha, it's again passed here, alpha. And this way we get the generator model, which is basically this one, which we created. It just runs the function and returns the out. Afterwards, we need to build a discriminator. And to the discriminator, we need to pass two types of inputs. Now, this is important. If you pass two types of inputs in TensorFlow, you will need to build two instances of the same object to be able to pass two different types of inputs. And that's why we're going to create two instances of the discriminator, but it has a parameter reuse. The first one is going to have a parameter false, but the one which we are going to create is going to have a parameter true, because it's going to reuse the previous weights. So then it's like just two instances of the same class that uses the same weights in the back. So it's not two separate discriminators, it's the same discriminator, but it has two instances because we need to pass fake images and real images. And for this to work, we need to have two instances. And that's what we're going to build now. So let's see the getDiscriminator function. Let's see what it returns. I think this is the one. Yeah. So it returns the out and the logits. And we can define, I've defined already them here, the names for the functions. And we do getDiscriminator again. And here, it's important. First, we pass the input real. Now we are going to pass the generator model because this is the output of the generator. Yeah, and this is what we're going to pass as input for the second discriminator. Reuse is going to be set to true to reuse the weights. And alpha, this is basic. And in this way, we have the fake model, the fake logits. Remember, the model is with the sigmoid function over it. The logits don't have the sigmoid function. This is the real part, and this is the generator model. So this is just building the generator and the discriminator. Now we have the discriminator cross entropy part. This is the part that builds the sum of the squared errors. This is the part in TensorFlow that's going to be able to calculate the error of the two types of networks, which we've talked previously about. And this is a little bit more complicated. So we need a smoothing parameter first. This is just, it's going to give me a value between 0.5 and 1.2. Then we need the labels. As we said, we need to encode the labels. So we need numbers for the labels. For example, cat's true, that means that we have 1. There's no cat in the image, we're going to have 0. And that's what we're building here with TensorFlow ones like. And we need it to be the same dimension as the models. And we apply the smooth parameter. This is for training again, for faster training. And this gets us the real labels. Yeah. So for the real images, we need ones because that's how those are the labels that we're going to use for the real images. After we get the labels and we smooth them, we're going to use TFNN sigmoid cross entropy with logits. Yeah, a long name. And here we just pass the logits, which are basically, this is for the discriminator. Yeah. And in our case are the real logits. So remember that this is the output of the network without the sigmoid function over it. And we pass them as inputs here. And we also pass the labels. Yeah, the real labels. And this part is going to compute for us this. Let me just show you. Yeah, this thing. So this is going to compute for us this entire thing in the backend. And afterwards, I forgot to mention here, this is the error for all the inputs of the network. But we need to update the weights with the error for only one input, for only one image. And that's why we need to take the mean squared error. So afterwards, after we take the sum of the squared errors, we're going to do the mean over them, and that's the value that we're going to use as the error. And that's what TF reduce mean does here. We do the same for the fake instance, as I told you. The smooth, the labels, this need to be 0. And I'm adding them, because multiplying with 0 makes no sense. And I'm adding them for the fake labels. And in the end, I'm using again the sigmoid cross entropy with logits. I'm passing the fake logits now, and the fake labels, and again reduce mean. Afterwards, there are going to be two instances. That means two different error outputs. And we need to concatenate them in TensorFlow, and that's how we do this. We use the dReal loss and the dFake loss, and that's the final error for the discriminator. Now let's do the same for the generator. It's more simple. I've just built the labels for you. Yeah, and now we need to build the cross entropy part. I'm just going to copy paste from here. And it's already defined. Generate the real errors. For logits, we're going to pass the fake logits. Now, this is important here. You remember that I said that the generator gets feedback from the discriminator. This is the part where that happens. The fake logits, it's the error from the discriminator that we calculate only for the fake images. Yeah? And that's the error that it's going to be used for training the generator. And then afterwards, we need to give as labels the ones that we created here, ones, because we want it to generate real images. And in the end, we do a reduce mean and hope it's going to work. And don't forget to pass the GVLA errors and return it as a parameter. So these are just wrappers over the networks. That's how TensorFlow works. It constructs an entire graph. We're not running it here. We're just constructing it, and it's going to be run in the session later. Let's see if something breaks. Nope. And now the last part, it's the optimization. So normally you could train it with gradient descent, but to make training go faster and to solve some problems with the training, there are all kind of types of optimizers that you can wrap the model of the training over. So for example, there's the stochastic gradient descent one, which is the most basic one, which would start. Then there's RMS prop and all these kind of other types. And we're going to use the Adam optimizer for this. I'm not going to go into details now. Basically, the Adam optimizer just uses also the mean for updating the weights and the step of the learning rate. Yeah, so the learning rate normally in gradient descent stays the same. You give it when you start to train the network, and you're not going to change. And the learning rate, if you remember, it's just the step of the step that the function will take to minimize the error. So if you remember the error like this, if you give a big learning rate, the step is going to be big. Now that's a problem, because if you have a function like this, that's okay. But if you have a function like this, then if the step is too big, it's possible that it's going to jump over the minimum, or if the function has a lot of local minima. And that's why you start to use all kind of optimizers. And the Adam optimizer uses AdaGrad. AdaGrad is an algorithm which gives separate learning rates for each weight in the network, for each parameter. So you don't have only one learning rate for everything. You have a separate learning rate for each weight. And also it uses what RMS prop uses, which means that it's going to use two other values: the mean of the error and the standard deviation, the variance of the error, to update the learning rate. Some people are going to sleep, so I'm going to stop explaining Adam optimizer. So let's go for it. What's important here? Let's see. Yeah. So for the model optimizer, first we need to take the trainable variables from the TensorFlow. So TensorFlow TF, it's the graph that we have. The graph that we built until now. And we are going to take all the trainable variables. Those are all the weights. And this gives us more than just the weights, because TensorFlow has other values that are trained. And we need just to take those that start with the discriminator and the generator. How do we do this? If you remember well, up here, when we created the discriminator and the generator, we had this with TensorFlow variable scope generator. This means that for each variable that we initialize here, for all the weights, they're going to start with generator. This is important so that we can filter them. And the same for the discriminator. And this is what it's going to happen here. We're going to filter just the values for the discriminator and the generator, because we need to pass them to the optimizer. And we do this, the vars and the g vars, the discriminator and the generator vars. This is a trick for TensorFlow to work. For dependencies, I'm not going to go into it now. And then you use the TF train Adam optimizer, where you pass the learning rate, which we have it from here. And besides that, you pass the beta, beta 1. This is the mean parameter that's used for the optimizer. And with the optimizer, on the optimizer that you created, you're going to run minimize. This is the function, the method where you pass the model. So this is the DLOS, the model that we created previously here. And DLOS and GLOS are going to be passed to it. And besides the model, you're going to also pass the variables that you want to minimize, that you want to train. And this is done with vals. So for the discriminator, we have dloss and dvars with d in front, and we need to do the same for the generator. So basically 2 lines of code, gtrain optimizer with learning rate and beta 1, same thing. And the second part is just gtrain minimizer, because this minimizes. And for this, we pass the gloss, gtrain, only change everything if you copy paste, and generator variables. And we return it. And normally, this should work. Yeah. So this is how we also pass the wrapper for the optimizer. This is how to some example to show the images during training. And then for the training part, we are left with 2 lines of code, which basically the first one is, so let's see the train model. This is just some pretty printing here. So we show every 100, we show every 100 epochs, this part, because if you show it at a lower value, then the training time is going to increase, because you just need to print out images each time. And it's going to print the error each 10 times. The steps we need for this part. Here we get the data shape. This is the images that we pass, and we get just the dimensions of them. After that, we get model inputs, which are basically the first function that we created. Let me check this one. We get the inputs. This is where we put everything together. We get the inputs. Afterwards, we get the model loss, which is through here. Yeah. And we need to get now the optimizer. So as you see, we get the model inputs, and the output from the function is passed to the model loss. So we pass input real, input noise, and learning rate we need for the next one. And we're going to do the same for the third function that we created, which is get model optimizer. And for the get model optimizer, let's see what it takes. It takes dloss, gloss, learning rate, and beta 1. I think beta 1 is passed here. Yeah, this is a long function. Doesn't respect any OOP principles. Okay, that should be it. And so we have the inputs. We pass them to the model loss to get the wrapper that computes the minimum of the error. And then we pass that model to the optimizer, which helps optimize all this computation in the end. As I told you, TensorFlow runs everything in a session. Basically, a TensorFlow session, here we create one with TF session as session, is handling all the GPU part, input part. So basically, TensorFlow with the session, it's handling how it gives everything to the GPU or the CPU, all the weights for training. So this is handled by the session. For all the variables, the weights, we need to initialize them in a session, and that's how it's done. We do session run, TF global variables initializer, and then we have the epochs, which are defined, are passed to the, are passed here somewhere. Let me check, epoch count, yeah. And we loop over the epochs, which is how many times you want to train the network with all the images, and you use batches. As I told you before, that's a number of images. Now, how big should be the batch? As big as possible, although you can play with it to see what the training does, but you can try to make it to scale it up until you're gonna get an out-of-memory error, because your GPU or CPU is not gonna be able to handle so much memory. We do a trick for rescaling. This is gonna help with the 10H function that we use in the end. We update the step, increment it, and now we build the batch noise. This is the part where we build the random noise for the generator as input. Yeah, so this is the input from which we're gonna build the images, the fake images. And it's between -1 and 1, and this is the size, the batch size and the noise dimension which are passed to the network. Some printing at the beginning, and this is the important part line. Session run, this is how you run the training. You pass the discriminator, yeah, which we get it from here. And afterwards, let me check where I am. Yeah, you give it a feedback. So if you remember, when we this function in the beginning get model inputs, we created just placeholders. We didn't give any values to those placeholders. So to give values to the placeholders, we need to pass them through a dictionary in the time that we are running. So here we do a fitdict. That's how TensorFlow works. We have input real, which is the batch images, which we get with get batches. Here we have batch noise as input noise for the discriminator, yeah, which is the one from here. And we pass the learning rate because that was also a placeholder. And now we need to do the same thing for the generator. So this is something that we're going to do together. Uncommented line if you want. We pass generator min. And as a fitdict, for the generator, we just need to pass the input, yeah, which is just the input noise, which we created in the first function. And I think batch noise, yeah, batch noise is the important part, and also the learning rate, yeah, learn rate. Take notice about learning rate and learn rate as the key and the value, not the best naming. Okay, and this handles the training, the entire training. And afterwards, we need to evaluate. So as I showed you up here, we are going to evaluate it every 100 epochs, and we do this by running it not on the minimizer. The minimizer is used for the training, but running it on the loss. So the loss is this one that we get from the model's loss, not on the model optimizer. That's important because the other one won't have the evaluation function. Believe me, Eugen can tell you because we stayed 2 hours for this to debug it. So this is important. And if you wonder who's Eugen, it's the guy from the room who helped me from Yopeso. I'm gonna answer questions at the end anyway, so if you have any. Okay, so we do this for the generator train loss, and we pass the G loss here. As input, we just need the batch noise. We don't need the input real because we don't pass real images for the generator. And I think this should be it. So let's see. Here we train it, and here we evaluate it, right? And I don't have any tests for this part. And here's the part where we start everything. So we give it a batch size, 64 images, a noise dimension, which is 100 by 100 it's going to be for the generator as input, the learning rate, the beta parameter for the add-on optimizer, the alpha parameter for the leaky ReLU, and the number of epochs. Here it's 2. Then this is just to get the data, and I have a wrapper dataset that also handles the pixel normalization between minus 0.5 and 0.5. As I told you, first we reset the default graph, because if we already created the graph before, we just reset it so that we don't have anything there. And we create a new graph with tf.graph, and we make it the default graph in TensorFlow, and we just run train model, and we hope that it's not going to break. Yeah, something important here. The data set class already has the getBatches method, the shape, the image mode, and the alpha. So this is the input for the generator with which the training started. Let me just check something. I'm curious if this is working. Yeah, so I've just left for a couple of time. This is running locally, so unfortunately you're not going to be able to run it locally and make faces with it. I mean, you can try, but it's going to take a lot of time. And for this, I'm using Floyd Hub, or you can use AWS or Google Cloud. And I've run this for, I've started this run when I started to speak. So that's 1 hour and something again ago. And let's just see this one if it's going to work. So remember, this is on the NIST dataset. This learns to predict images with numbers. Yeah, but I run it on the faces part, and you can see this was the input for it. And here it's just printing the loss and the discriminator loss and the generator loss. And afterwards, it starts. The generator starts to generate some kind of contour of the faces. This goes on, goes on, on. And if we, let's just scroll to the end, or at least wait, I think it's still training. Yeah. So as you can see, the faces from here start to be really, really more real, sometimes at least. Let's see. Yeah, those are the last ones. Those are kind of scary. Let's look at these ones. Yeah. So as you can see, just after 1 hour and something, it's able to generate novel faces. So those are not faces from the celeb A, although they look like celebrities. I'm going to let you figure it out, that part. Now, another important part. These images are really small. And the reason for this is that because we can train them on locally or on a GPU in a short time. But last month, in October, the guys from NVIDIA were able to plug this as input noise. And after some weeks of training, they got this part, which are 1,000 over 24 images per 1,000 over 24. And you can see that some of them are really good, like this one. And this one has some, I mean, I think it was beaten, also this one from here. But you can see that things are really advancing. I've put here the paper, and they also have a training video. If you're in time, we can just look a couple of seconds to it, just to make an idea. Let me think. Yeah, I can get it faster, way faster. So yeah, these are the images made, but I don't want this one. I want the other one with... Yeah, the other one was really cool. It's, look, yeah, so this is actual training from the generator. Okay, that's too fast. So this is how it's able to learn in time, but this is after quite a lot of time. I mean, it took weeks. I think this is the one with the, let me just check, yeah. Okay, and somewhere it should see the pixel part. I don't remember where. But you can find it. There's a cool video where it shows the training, how it happens from the noise part, and it gets to these images. So those are all images created with GANs. And I've put some resources here, like the main paper from Jan Goodfellow and the tutorial from him. This is also a paper. There's a paper on improved techniques, some really cool GitHub things. So for example, I didn't tell you anything about what you can use GANs for. So you can use GANs for things like generating faces, as we did now. You can use GANs for generating the next frames in a video, for example. So this is another part where there are guys who are trying to create small movies with GANs, using GANs. You can also use GANs. As you can see, there are a lot of research papers on it. So you can take a look at this part. A pretty cool one is the pixel-to-pixel one. Let me just check it. GitHub. But I think it's pix-to-pix. GANs. Yeah, cycle GAN or the other one. Yeah, so as you can see, but this is, I think, some example for someone who tried it. Pix-to-pix. Yeah, this is the one. So this is really cool. You can check it out if you want, because it's able from inputs like down from here to generate real images, like the output from here. Or you give an input like this and it generates an output like this, more vectored stuff. Or make from day to night. Or from a drawing, and this also for cat or anything, and it gives you a real image. Now GANs are used also for two really cool applications. One is the classification part. So they are used in semi-supervised learning, for example. They can boost a lot of training of a classifier. And even a cooler one is, I think OpenAI does this. They use it in they try to create with GANs reinforcement learning context for different algorithms. So they use GANs for creating them. And definitely you can use GANs to enhance the data set. So if you have a data set with only an n number of images, you can use them for creating other images which maybe if a human will look at them, they won't be really, really all of them real, but for a computer, it's more than enough to train. So this should be it from my side. And if you have any questions, yeah, so I don't forget. Sorry. Last slide. Special thanks. This is really important for me, especially Corina. So all those cool animations that you saw were made by Corina. She's a designer from Yopeso, and I really need to give her some special thanks because she worked really, really hard a couple of days to make them work together with me. Also, thanks to the Yopeso team. Some of them are here. They really helped me on debugging all the parts and constructing the presentation. And also special thanks to Udacity. Most of the intuition that I've presented you here, it's taken from the courses that I've previously taken through Udacity. And after that, digging even more. But I think that if you really want to start to learn this part, that's the place where you can start to go, even if you have you don't have any experience. So that's really cool. And they also gave me some scaffold for the architecture code, which I've used for the training. So that's all from my part. I think if you don't have questions, definitely.